an area in both tails. Uniformly most powerful is a topic that is very important to understand. It comes up a lot, and it's also potentially confusing for a lot of students, but really it's not that hard. Basically what it says is that a test is uniformly most powerful if you have a single rejection region for the test. So your rejection region, you just have a single rejection region for all different values of your alternative. So I should have mentioned that uniformly most powerful tests apply to a composite alternative, which means that your alternative can take many different values, and so and a simple null. So you get a rejection region when you take a simple null and a simple alternative, right? That's by LRT. And so say that for every possible alternative, you would get the same rejection region. In that case, your test is uniformly most powerful. It's uniformly most powerful. It's because by the Neiman-Pearson lemma, we know that LRT is most powerful for simple tests, and we're getting the same rejection region for all of these simple tests, and hence our test is going to be most powerful for all the different alternative values that you can have. So we looked at an example here of the Laplace distribution, and it's really important you understand this picture. From this picture, you should be able to see that your rejection region is going to be in purple here. It's not obvious that it's -3 to 3, but it should be obvious to you that you would be rejecting in the purple region because in close to 0, it's more likely that you're in the null distribution, whereas outside in the tails, it's more likely that you're in the alternative distribution. So it's in that outer tail region that you should be rejecting the null. So if you understood that, then this is just all a bunch of calculations, and we just calculate what the rejection region specifically is using the fact that alpha is 0.05. Now, we're going to check that it's uniformly most powerful test between for your alternative between 0 and 1. So you go through this computation here, and you see that at every step you are either requiring the b be greater than 0 or less than 1 to get that we're going to reject when the absolute value of x is greater than 3. So that proves that our test reject when absolute value of x is greater than 3 is uniformly most powerful. Now when b is 2, you can check that you're going to get a totally different rejection region. You're going to be rejecting inside around 0, and you can check that this will be the same rejection region for any value of b greater than 1. So in that sense, our test is either uniformly most powerful between 0 and 1, or greater than 1, but not greater than 0, because we have a change in the rejection region right at when b is 1. For your homework, for your next homework 3, you're going to be drawing a power curve. So here I just basically introduce this to you. You're just basically graphing the power as a function of theta. I should have written here theta. So for every value of theta, we can compute the power. Technically, when theta is 1 in this case, this is the that is the null hypothesis. That's the null distribution. But we can also compute what the chance of rejecting the null is when the null is true, and of course that's just alpha. So at 1 we get alpha, and here I just compute, for example, what the power is at a half. Then finally we wrapped it up with something that's really obvious if you think about it, and that's the duality between confidence intervals and hypothesis testing. Basically, if you have, let's say, IID normal, let's say this scenario here, mu 0 is the null and some composite alternative. So you have this picture here. Then when would you reject? Well, you're going to reject when you're in the tails, right? You're going to reject when you're in the tails. What I'm drawing here is the null distribution. So you're going to reject the null. You're going to reject the null hypothesis when under the null distribution, your test statistic, which is the sample mean here, is very large or very small. And you're going to accept when your test statistic is between what I've written here, right? And so that is what hypothesis testing is, right? But this is very deep, so brace yourself. If you just do this little bit of algebra here, you can see that you can just rewrite this inequality so that you have mu naught in the middle, and that is 101 minus alpha percent CI for mu. So now in this, so that's the duality right there. It's basically these two lines. Now to do this completely generally and not in a specific example, you need what's called abstract nonsense. And so if you would like an introduction to abstract nonsense, I'm sure Dimitri would appreciate that. You should read theorem A and B in section 9.3 and